Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 4.3 and looking at complex characteristic roots and underdamped harmonic motion. In Chapter 4.3, we will complete our descriptions of the solutions to linear second-order homogeneous differential equations with constant coefficients by looking at the case where the roots to the characteristic equation are complex. These solutions show underdamped oscillations in spring mass systems, guitars, pianos, and RLC circuits. Graphically, we can see that underdamped motion shows oscillations around your equilibrium point with a decaying amplitude. In solving linear second-order homogeneous differential equations of the form ay double prime plus by prime plus cy equals 0, we determine that the characteristic equation ar squared plus br plus c could have three different types of roots. Two distinct roots, which led to overdamped motion. One repeated root, which led to critically damped motion. And now today we're looking at the case where you have two complex roots, and this leads to the underdamped motion. Now in today's problem, the characteristic equation will not be factorable, in which case we'll have to find the roots of the characteristic equation by using the quadratic formula. If we're going to have complex roots, it will be when the discriminant, the b squared minus 4ac, is less than 0, meaning that we will be taking the square root of a negative number here, which will lead to the imaginary number I. And so in general, we'll be able to simplify this expression to give us some kind of a general complex number. And so for now, I'm going to represent the terms of the complex number as alpha plus or minus I beta. However, in actually doing the problems, we will notice that we will only be using the alpha plus I beta when we are writing our solutions. And I will make an argument for why that is the case, but our author and in class, we will always use the positive root when looking for our general solution. So this is going to be the value of R, our complex characteristic roots. So now we ask, what will solutions with complex characteristic roots look like? So remember, in general, we said solutions are of the form e to the RT. But now we have found that R is a complex number of the form alpha plus or minus, or alpha plus I beta. So let's explore this solution and see what we can develop. One of the first things you'd probably want to do is distribute the t into the parentheses. And so we can write our exponential of the form e to the alpha t plus I beta t. Using rules of exponents, we can rewrite this as the product of two exponentials of the form e to the alpha t times e to the I beta t. Recall that when you're multiplying two exponential expressions that have a common base, we add our exponents to obtain our previous line. Now this expression can be rewritten by Euler's formula. And Euler's formula is going to be developed in your homework. But the Euler's formula says we can rewrite the e to the I beta t as cosine beta t plus I sine beta t. And this is by Euler's formula. Let's continue to simplify this expression. We could distribute the e to the alpha t to each of the terms inside the parentheses to obtain e to the alpha t cosine beta t plus I times e to the alpha t sine beta t. Where this portion is referred to as the real portion, and the second part, not including the I, this is the imaginary portion. And one of the problems in our homework asks us to verify that the real portion and the imaginary portion are each individually solutions to the differential equation. Individually solutions to the DE. This allows us to say that a basis for the solution space of the differential equation is going to be e to the alpha t cosine beta t and e to the alpha t sine beta t. And then a general solution would be written as y of t is equal to c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t. And this is by the superposition principle, that the sum of two solutions is a solution, any multiple of a solution is a solution, and in general, any linear combination of solutions are solutions. In application, when using this general formula, we will usually factor out the common factor of e to the alpha t and write our general solution as c1 cosine beta t plus c2 sine beta t. And this will be the starting point for the majority of the problems that we look at. Now, what I provided here for you is a method for verifying solutions. And so if you wanted to verify that e to the alpha t cosine of beta t is a solution to this case, we could evaluate this by using direct substitution. And I encourage you to go through the next page and a half to verify that this e to the alpha t cosine of beta t is a solution. However, I will not be going through this in our video today. I presented this here just for completeness and for you to verify without having to do the algebra yourself that this is indeed a solution. So please take some time to look through this verification. It is a little bit long, but I believe everything here is at a level that we should be able to follow nicely. I would like to jump right into an example. So let's turn to page 21 of our guided notes. And consider a spring mass system that has a mass of 1 kilogram attached to a spring with a constant of 5 newtons per meter on a table whose friction coefficient is given by 4 kilograms per second. Find the equation of motion for the spring mass system if it is pulled 0.1 meters to the right and then released from rest. Okay. Let's start by writing our initial value problem. Remember, the initial value problem is your differential equation along with the initial conditions. So here we want to remember the form. It's going to have the mass is 1 kilogram, so that'll be 1 x double dot, and I'm leaving the 1 off, plus your coefficient of friction, your damping term, so plus 4 x dot, plus your spring constant, 5, x equals 0. Our initial conditions, that your displacement, your position at time 0 is the 0.1 meters. And x dot, your initial velocity, because it's released from rest, is equal to 0. we can jump to our characteristic equation. Remember, your characteristic equation is going to be a quadratic in R whose coefficients are the same as your dE. And notice that this is not going to be factorable because there are not two numbers that multiply to 5 and add to 4. So this is not factorable. We would have to use the quadratic formula to obtain R is equal to the opposite of B plus or minus the square root of B squared, which I'm going to just write as 16, minus 4. A times C is going to be 5. All over 2A. Notice the discriminant here is going to be 16 minus 20 or negative 4. So we're taking the square root of a negative number, which will introduce imaginary numbers. So I'll write this as negative 4 plus or minus 2i, because the square root of 4 is 2, and the square of the negative number brings the I, all over 2, which we can write as negative 2 plus or minus I. Now we are just going to use the positive version of this complex number and say that in our general form that we're looking at, the alpha, this is negative 2, and the beta, that's just 1. This allows us to write the general solution to our dE. Now remember our form. Let me scroll back for a minute. The form of our solution is going to look like e to the alpha t times c1 cosine beta t plus c2 sine beta t. So now that we have our alpha and beta, let's just directly substitute those into the form of our solution. To get x of t is e to the negative 2t c1 cosine a beta t, which is 1, so cosine of t, plus c2 sine of t. And this is now the general solution to our differential equation. However, we had an initial value problem, so let's go further to solve for our constants. And remember, for our initial value problem, we were given two values, two conditions. One was on your initial position, or the displacement of your spring. One is on the initial velocity. And so we need a velocity function now. So let's find x dot. When finding x dot, one of the common mistakes that students make is not to recognize that this is a product of two functions. Here's an exponential function times a combination of cosines and sines. But this is, because I factored it, this is a product. So we need to use the product rule when finding our derivative. So here we go. The derivative of the first function. The derivative of e to the negative 2t is e to the negative 2t times by the chain rule, the negative 2, which I'll write in front. The second function stays the same. plus by the product rule. I'm going to write down the next line so I can probably fit it right here. Plus by the product rule, the derivative of the second function times the first. So here, the derivative of the second function, well, I'm going to write the first function first to keep these exponentials in front. And now we'll write the derivative of the second function. The derivative of c1 cosine of t is negative c1 sine of t. And the derivative of c2 sine of t is going to be plus c2 cosine of t. So again, take caution when writing your derivative to use the product rule here. Now, since our initial conditions are at time 0, let's evaluate our position function at time 0, and then we'll evaluate our velocity function at time 0. When we evaluate our position function at time 0, notice you're plugging a 0 in for t. So this is going to be 0 as an exponent. And similarly, cosine of 0, this is going to end up being 1. And sine of 0 is going to end up being 0. So I think when we simplify this, you have e to the 0 is just 1. Cosine of 0 is 1. So I think it just ends up being c1. And sine of 0 is 0. And by our initial conditions, this has to equal to 0.1. And now we'll evaluate our velocity function. When you evaluate at 0, notice on this kit one, our exponential is not just 1. There's that coefficient of negative 2 now. So yes, e to the negative 2t, this turns into 1, which means our coefficient is now going to be negative 2. Again, we evaluate at 0. Sine of 0 is going to be 0, so this whole term goes away. So we'll just have c1 times cosine of 0, but that cosine of 0 is 1. So we just get negative 2c1. On this second term, again, this is sine of 0 is going to be 0, so that's going to go away. E to the 0 is going to be 1. Cosine of 0 is going to be 1. So I think this second portion just turns into plus c2. And from our initial conditions, this has to equal 0. From our first equation, we can directly find that c1 has to be 0.1. And if c1 is 0.1, then the second equation tells us negative 2 times 0.1 plus c2 has to equal 0, which tells us c2 has to equal to 0.2. With these constants, we can now write the solution to our IVP as, let's just plug C1 and C2 into our general solution. To get x of t is going to be e to the negative 2t times 0.1 cosine of t plus 0.2 sine of t. And this will be the solution to our initial value problem. However, I don't like writing my solutions in this form since I know that this is going to look like some trigonometric expression. It feels nicer if we can rewrite what's inside the parentheses as just a single trig function. So let's use our conversion method to rewrite this as a single trig function. And remember, the way we did this is we used a triangle to remember the method. And in this triangle, it's a right triangle, you always put your first constant, 0.1, on your horizontal portion of your triangle. The second constant, 0.2, on the vertical side of your triangle. Remember, A, your amplitude is always on the hypotenuse, and your phase angle, delta, is always this angle here. So that we can say A, your amplitude, has to be the square root of the 0.1 squared plus the 0.2 squared. And if you grab your calculator, I believe this should end up being the square root of 0.5. Let's verify that real fast. Grab your calculator. So we have the square root of 0.1 squared plus 0.2 squared. And this should be, well, let's see if I simplify that. Let me just do the 0.1 squared plus the 0.2 squared first. So that's going to be the argument inside of our calculator. Oh, it's not 0.5, it's 0.05. .05. I'm glad I checked that. Or approximately 0.224. And then remember, delta, our phase angle, is going to be the arc tangent of 0.2 over 0.1. So make sure your calculator is in radian mode here. And we'll do the arc tangent of 0.2 divided by 0.1. Which should be 1.11. Okay, this allows us to rewrite the solution to our IVP as x of t is e to the negative 2t. That part will stay the same. But the portion inside the brackets we can write as 0.224 cosine of t minus 1.11, where we have rewritten the portion inside of the brackets as a single trigonometric function. However, I'd like to do one more portion still to this. We can factor out or rewrite this so that the 0.224 is on the outside. And so we'll write this as x of t is e. Oh, let's do the decimal first. As 0.224 e to the negative 2t cosine of t minus 1.11. And this would be what I would like to write as the solution to our initial value problem. And what you'd like to notice is that this is a trigonometric function where the amplitude is changing over time. So this portion here is sometimes referred to as your time varying amplitude. As time goes on, the amount of your amplitude, the value of your amplitude is changing. And specifically, you can say it is decreasing over time. Because of that negative exponent on the exponential term here. So this is a decreasing amplitude trigonometric function. And this should give a little bit of insight to why we know this should make sense. Remember, we were talking about the graph of a damped harmonic motion that started 0.1 meters from equilibrium, and as time goes on, the amplitude of our trigonometric function, our oscillations, is going to decrease. So it makes sense it should look something like this. Okay. Let's try another problem, but let's apply it to something that we're familiar with. So other great examples of damped harmonic motion is the vibrations of a guitar string or the vibrations of the strings in a piano. The same differential equation applies, but these models have the attraction that you can hear them. We can model the sounds of guitar string as a spring mass system where the vibrations of the string are in a plane parallel to the neck of the guitar. So if you're not familiar with guitars, this is referred to as the neck. And so when you pluck a string on a guitar, the string will show vibrations. So let's look at an example. Actually, and I just thought in Canvas, there are some great resource videos that show you the visualizations or that shows you how a guitar string vibrates over time. So if you haven't done that yet, make sure you go and look at the resource videos. Showing the vibrations of a guitar string. Now, I think they're really interesting videos and something that you'll probably get a lot out of. But let's look at our example here. Consider the motion of an underdamped guitar string described by the DE x double prime plus 2x prime plus 26x equals 0, with the initial conditions that your initial displacement from equilibrium is 0.01 meters and your initial velocity on your guitar string is 0. So this would be the scenario where you pull the guitar string and just let it go, not imparting any initial velocity. Of course, since we're given the differential equation already, we don't have to write the differential equation. We can jump right to the characteristic equation. So remember, your characteristic equation looks the same as your DE, but written as a quadratic in R. And as I was about to just start writing this, I thought I should stop and actually give you a moment to think about this on your own. So if you could, pause your video and try and working on this DE yourself and come back maybe as far as you get to the general solution. Write the general solution of your DE and then come back and we'll see how you did. I'll see you in a moment. Okay, let's see how you did. So our characteristic equation would be a quadratic in R whose coefficients are the same as that of the DE. Again, observe that this is not going to be factorable. There are no numbers that multiply to 26 and add to 2. So we'll use the quadratic formula to obtain R is equal to, recall it's going to be the opposite of B plus or minus the square root of B squared, which I'll write as 4, minus 4AC, which is going to be 26, over 2A, which is just 2. Here, the discriminant is going to end up being 4 minus 104, or just negative 100. So notice we're taking the square root of a negative number, and the square root of negative 100 is going to be, will give us negative 2 plus or minus 10I over 2, which if we simplify, we can write this as negative 1 plus or minus 5I. Of course, we need to recognize here that alpha is going to be the negative 1, and the beta is going to be a 5. These are the two parameters that we'll use in writing our general solution. So I hope you have written this as x of t is going to be e to the negative t times c1 cosine of 5t plus c2 sine of 5t. And this is going to be your general solution to your differential equation. But remember, we were given an IVP here. Our IVP gave us an initial condition on position and an initial condition on velocity. So let's go find our velocity function. So x prime of t. And again, I want to remind you, and this was a common error for lots of students in the past classes I've had, is they don't recall or don't recognize, or they're just in a hurry to not recognize that this is the product of two functions. You have an exponential function times these trigonometric functions. So this is the product of two functions. We need to use the product rule. So here we go. The derivative of the first function, the derivative of e to the negative t is e to the negative t times by the chain rule, negative 1. The second function stays the same. And then it's plus by the product rule. The derivative of the second function times the first. I like writing the first function right away, though, so I don't forget it. So I'm going to write the e to the negative t right away. And now we'll take the derivative of the second function. So remember, the derivative of c1 cosine of 5t is going to be negative c1 sine of 5t times by the chain rule, the derivative of the inside, which gives us a 5. Plus the derivative of c2 sine of 5t is going to be c2 cosine of 5t times by the chain rule, the derivative of the inside gives us another 5 as a coefficient. So here's our derivative by the product rule. Of course, we now want to evaluate both of these at 0. So now we'll write x of 0 and x prime of 0. And remember, when you evaluate that this is 0, a lot of these expressions or terms are going to go away. For example, when t is 0, you have this e to the 0, which ends up just being 1. And if t is 0, you're going to have sine of 0, and sine of 0 is just 0. So in this first equation, I think we just get C1. And from our initial conditions, we know that this should be 0.01. When we evaluate our velocity function as 0, again, remember a lot of these terms go away. If t is 0, this e to the 0 ends up being 1 times your coefficient -1. And sine of 0 is going to be 0. And cosine of 0 is going to be 1. So I think this first one just gives us negative C1. Our second term over here, again, e to the 0 is just going to be 1. Sine of 0 is going to be 0. Cosine of 0 is going to be 1. So I think this one ends up giving us 5 C2. And from our initial conditions, we know this has to be 0. From our first equation, we could immediately C1 has to be 0.01. And if C1 is 0.01, then our second equation will give us something that looks like this, that we can solve for C2. I think C2 will end up being, we'll move the 0.01 to the other side. We'll make it positive 0.01, and then we'll divide that by 5. So let me grab my calculator real fast. So 0.01 divided by 5 is 0.002. So that's our value for our second constant. And with these constants, we can rewrite these our general solution. So I think our general solution, or the solution to our, not general solution, the solution to the IVP will end up looking like x of t is going to be e to the negative t 0.01 cosine of 5t plus 0.002 sine of 5t. And this will be our first equation of the solution to the initial value problem. However, like before, I would like to be able to rewrite this as a single trigonometric function rather than having this bracket having the combinations of sines and cosines. So recall the way we do this is using that triangle tool. So if I were you, I would draw your triangle, label the sides of your triangle, and rewrite this as a single trigonometric function. And maybe this is again where I'd ask you to pause your video and find your single trigonometric function representing this expression. I'll see you back here in just a moment once you finish doing that. Okay, let's see how you did. I'm hoping you put your C1 constant on the horizontal side of your triangle, your C2 constant on the vertical side of your triangle, and recall that your amplitude is going to be the hypotenuse, and your phase angle delta is going to be this angle. So that we can say A, your amplitude would have to be the square root of the 0.01 squared plus the 0.002 squared, all that square rooted. Let's grab our calculator. So it'll be 0.01 squared plus 0.002 squared. So this is just what's inside your square root. And then I'm going to want to take a square root of that. So square root of your answer. I'm going to hit second answer. And I think if we write our decimal to 4 places, it should look like 0.0102 is our amplitude of motion. And remember our phase angle now, delta, is going to be the arctangent of C2 divided by C1. So here, arctangent 0.002 divided by 0.01. And again, I'm going to write this one to maybe 3 decimal places. So how about 0.0? Nope, that's not a 0. 0.197. This is going to allow us to rewrite the solution to our initial value problem as e to the negative t, and it's going to be 0.0102 cosine of, now it's going to be 5t minus our phase angle, 0.197. Again, I would like to rewrite this expression without the brackets and combine terms, or change the order of our terms. So I want to write this as x of t 0.0102 e to the negative t cosine of 5t minus 0.197. And this is the solution to our initial value problem that I would like to use. Again, one of the things that you'd like to notice with your solution is this portion, the exponential on that constant. This would be your time varying amplitude. You will also see, when you read our textbook, that they sometimes refer to this as the envelope. If you grab just your time varying amplitude and write y equals the 0.0102 e to the negative t, and let's call that y1, and y2, the negative version of this, e to the negative t, that these two functions create what they refer to as the envelope, describing your decreasing amplitude of your damped harmonic motion. Let's actually go and grab some kind of a graphing calculator so we can see what this actually looks like. And so I'm going to go to our Canvas course. And let's go to maybe Desmos. I really like Desmos. Now the function I want to graph is our solution we just found. I'm going to write it as y equals. Our time varying amplitude was the 0.0102 e raised to the negative t cosine of 5t minus 0.197. Now, maybe a lot of what you see here is unnecessary because you have your vertical axis. This is t equals 0 in the middle, so everything going on to the left doesn't really make sense for us to talk about for negative time. So how about we change our viewing window that we're looking at. Now, to change your viewing window, click on the gear icon or the wrench icon up in the upper right-hand corner. Now remember our y scale, we started with a displacement of 0.01. So maybe on our y-axis, let's go to from negative 0.015, so a little smaller and a little higher. And I think I forgot the negative on my first one. And let's also change our x-axis to start at time 0. So this is what we should see as the graph showing the displacement of our guitar string, starting with an initial displacement of 0.01 meters, and then as time goes on, your oscillations will decay. Now, if you'd like to add to this your time varying amplitude or just the envelope, we can graph in here y equals 0.0102 e raised to the negative t, and also maybe y equals 0.0102. Well, let's put a negative in front of this one. Negative 0.0102 e raised to the negative t. So notice here the blue and the green lines are not part of our function. They're just showing the envelope that is the boundary of our time varying amplitude. So maybe let's add this to our guided notes for a visualization. So let's draw our vertical axis, our horizontal axis. Let's label this one x of t and t. We started with an initial displacement of 0.01 meters, and then we saw as time goes on, our amplitude would decrease, and so our graph would look something like this. If you'd like to add the envelope, our envelope would have been some decreasing exponential functions that met the maximum and minimum values of your decreasing amplitude cosine function. So it looks something like this. So this would be y equals 0.0102 e to the negative t, and y equals negative 0.0102 e to the negative t. These are what create the envelope that bounds them. Okay, I'm going to end our video here. I hope this is helpful. There are a couple other examples in your homework you get to look at. There's even some ones that talk about RLC circuits that you'll recall from your last section, chapter 4.2. But I think this is enough for this video. I hope this is helpful, and I'll see you next time.